So thank you everyone for joining. My name's Kavita. I've been the one that's been sending all these emails about everything. And today I'm going to be presenting on some work that's been conducted at the University of Illinois. The primary graduate student working on this is actually Stephen, but we are currently having a laser service visit ongoing and he's supervising this. So I'll be giving this talk in his stead. So I know this title, you're seeing all these words, stimulated Brillouin scattering. You might be asking, what does this have to do with fusion? This talk today is focusing on the laser drivers for fusion. We'll be talking about some amplifying or amplification methods for laser drivers. So we will dive down a little bit into this title later. This work has been a collaboration with many people. The project originally started with Exemer Energy, and they funded the original part of this work. And now the RISE Hub is currently supporting us. And we're also collaborating with the University of Alberta. So at any time, if you have any questions, please do not hesitate to ask. You can just unmute yourself. If you put them in the chat, it might be a little hard for me to look at it, but I will do my best. So, like I said, what am I talking about today? Laser drivers. So I'm going to first go over some of the laser drivers for fusion energy, and then I'll turn our attention towards gas lasers and laser amplifiers. I love gases. And then we'll get into the actual breadth of the talk, which is really the stimulated Brillouin scattering. So I'll introduce some of it and talk about our experimental results and get a little bit into the theory. Muzzlemal will talk more about the theory later this year. He is working very extensively on it. And then I'll share some of our future experimental plans. So there are a lot of things we need to consider when we're making laser drivers for fusion energy. One of the biggest things we need to look at is the wall plug efficiency. So the wall plug efficiency, the reason it's so important is we're trying to make this power plant. And so with this power plant, we need it to actually be sustainable. We can't have the laser driver use more energy than we're getting out of the gain medium. And so this is something we're really, really working towards. And it's not just how efficient, the energy in versus energy out. It's the energy in for the whole system. So we're talking any cooling systems and vacuum pumps, all of that comes into play. And the number that we see a lot for what we kind of need for a laser driver is or for LFE is about 10%. But higher will be better. Any improvement we can make to get above that number will be great. One of the biggest and most important things we need to think about is the wavelength. The wavelength for these systems needs to be less than 400 nanometers. And there's several reasons why. The two biggest ones are really the coupling efficiency to the target. The shorter wavelengths just couple more effectively. And then the other benefit of getting to shorter and shorter wavelengths is that we're preventing a lot of our plasma instabilities, all these deleterious processes that we don't want going on. Something else that's really important is the laser line width. We want something broad. And the reason is it's also going to help prevent some of these plasma instabilities. The number that we see a lot is something greater than a terahertz. But again, bigger is going to be better. Broader will be better for us. The rep rate, we need, again, to make this like an actual system, we can't have one or two shots a day. We need something that can be able to be fired repeatedly without damaging the system and without hurting the wall plug efficiency. So that could happen with if we're generating too much heat. The number I see a lot for repetition rate is somewhere, I see 10 hertz a lot, but really anywhere between 1 to 10 hertz is probably going to be ideal. And with that repetition rate, the biggest limitation is actually thermal management. The more often you fire your laser, the more heat you're going to be generating. And so there's this kind of trade-off that goes on with this system. And so how do we actually cool these lasers effectively so we can increase our repetition rate and not hurt our wall plug efficiency? These things are all coupled to one another. The beam shape of our laser is really important. We want a good beam shape. The cost. This is supposed to be a fusion power plant that we can use to actually supply the power grid. So if it's going to cost us $1,000 per shot or $1 million per shot, that's not going to be affordable for the community. So we're trying to keep these costs as low as possible. Energy range, we're looking at megajoule lasers right now, kilojoule megajoule lasers. So these are pretty big beasts. The temporal pulse profile is also really important. We want these pulses to be short so that we can have high peak powers. So looking at least probably on the picosecond scale, but we can work with shorter too. And lastly, we need a small nonlinear index of refraction. That's just going to help with some of the nonlinear processes that are going to go on. So there are a lot of different laser systems that are being looked at for fusion. And I don't have all of them listed. I have the three that are probably the most talked about within our hub. We're not working on ND glass in the hub, but this is what NIF uses. So with NIF, they have optical fiber lasers, 192 of them. And I can't remember if it's erbium or ytterbium. I don't remember which one. Probably ytterbium. And what happens is they have all these fiber lasers, and then they're going to amplify them with neodymium glass. And this is just a really, really pretty glass, like they're glass amplifier slabs. I love looking at ND glass. I love the pink that you can see in there. And ND glass, that lasers at 1053 nanometers. So, you're looking at, oh, hey, on the previous page, I said we need to go to shorter wavelengths. Well, that's why we frequency triple it down to 351 nanometers. Um, Another system that is being considered, and this is something that both Exemer Energy is working on, as well as the Naval Research Lab. So this is within our hub, are the krypton fluoride and argon fluoride systems, so our rare gas halides. And these operate in the UV, so 248 nanometers and 193 nanometers. And they have different amplification methods that we're using. So at NRL, I know they're primarily looking at krypton fluoride and argon fluoride amplifiers. And at Exemer, they're looking at SBS, which is what we'll be talking about today. Another system that we are looking at for fusion is the TISAF system. So this is what Marvel Fusion is working on in collaboration with CSU. So they're using the system, it's a femtosecond system, and they're using it with the nanowire targets. And I won't go into too much detail on this, but Jaden is giving a talk next month. He is a graduate student in Professor Roca's group, and he'll give more information on this next month. Now, there are so many other systems, like I said, that can be used and have been considered. For example, the CO2 laser was considered a lot back in the 80s. It checks a lot of boxes off. It is really good with heat management. The wall plug efficiency, which has not been optimized, is like 40%. And so it honestly seemed like a really promising system. But the biggest issue it had was the lasing wavelength was 10.6 microns. It is way too long. They were not able to effectively couple this to a target. NIF was looking at this system for a while, and so they eventually scratched that idea. Now, the wavelength isn't the only consideration. There's so many other parameters, and so many systems have eventually been scrapped because they just can't work. But I think that it is worth it to look into every system until we really rule out that we can't use it. So there are a lot of great systems. I like my gas systems. So I do like the CO2 laser, even though we can't use it. So there's, again, advantages and disadvantages for every system. There's not one perfect laser driver. But gases are really, really nice because you can't damage them. I really, really would love if someone finds a way to damage a gas, please let me know. But they what happens in a gas if you put too much energy, you're just going to break it down. You're going to make a plasma. So that's really, really great. We're not actually going to hurt our gas gain medium. And in addition to that, gas is just a really great for dealing with heat. You're getting collisions, right? It's going to dissipate your heat. And because of that, we can have higher pulse energies and we can have higher repetition rates. So 1 to 10 hertz. Another good way of cooling down gases is just circulating it, just circulating your reservoir. So you don't have to deal with water-cooled systems or fans. It's actually a lot easier. Beam quality is great for gas lasers. You're getting an M squared of almost 1. And this picture right here, it's just a really cool picture. But this is an argon ion laser. And I guess there's a service rep or someone that's tuning something. But the beam quality with these lasers are so great that you can use it to image and analyze so many systems. So I think he's doing some spectroscopy on this painting. And another great advantage for these systems is you can control the pulse profile. So our work is today, we're going to be focusing on amplifying the rare gas halide laser systems. So I thought I'd take a few minutes and kind of just explain how these systems work. Now, this plot to the right, I love this area of physical chemistry. So if you have any questions at all after I explain it, please let me know. Krypton fluoride and argon fluoride are exomers. And I'm not sure if everyone here knows what an exomer is, but it's a molecule that only exists in an excited state and it's transient. So what exactly does this mean? Well, I'm going to refer us to this plot here on the right. Let me get a little laser pointer here. So this is what's known as a potential energy level diagram or an interatomic potential curves. So on the x-axis, we have what's known as the internuclear separation. So it's the separation between two atoms. And on the y-axis, we have the energy. So what does this exactly mean? So this right here is the ground state, and this is the excited state. So in the ground state, right, we have two atoms. If you push two atoms really, really close to one another, they're going to want to repel. You know, the nuclei, they're both positively charged. They don't want to be next to each other. So it's going to require more and more energy to get them closer and closer to one another. And they're never going to actually touch. This is where zero is because it's not possible. I mean, that's fusion right there. And when the two atoms are really, really far apart, they're going to do nothing with one another. They're going to have no interaction. And we can see here, there's really no minimum. In an exomer, it does not want to form a molecule. For molecules that are actually stable in their ground state, for example, nitrogen or oxygen, you're going to see something like a well in the ground state, something like this that goes below zero. And that's because they want to form a bond. Nitrogen forms a triple bond, oxygen forms a double bond. And so it's actually going to require to put in energy to break the bond. And we don't see anything like that here in the ground state. So that's just one way you can use these curves to kind of see how strongly bond or weakly bonded are your molecules. So let's talk a little bit more about how you form krypton fluoride. So like I said, krypton and fluorine, they don't really want to form a molecule. But what we do is we excite krypton, and you can do it with e-beams, a discharge system. Anyway, it does not matter how you excite krypton, you just have an excited krypton atom. And that's going to actually collide or have a collision with fluorine. And this is known as a harpooning reaction. And what happens in this collision is that we're going to form a molecule. So it's going to be KRF star in this state. And this is a bound state. And we're going to get emission from here down to here. So we'll emit a photon, and then krypton and fluorine will separate. Now, this transition, which is really helpful for us, is in the UV. And like I said, this is a little well. And so what happens is you're going to get all these vibrational and rotational modes. So you're going to get lasing from a state here, 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 keeps going on. And because of that, it's a molecular transition, and it's going to be broad. Are there any questions so far on any of this? That's a great question. So Richard asked, what types of pressures do you need? So for KRF, and we literally have the services right now on our krypton fluorine system. So I'm seeing anywhere for our systems between like 0 to 100 psi. At least that's what our regulators are rated for. But I actually am not entirely sure. So I will write that down and get back to you.
Thanks. I was just wondering because it seems like higher pressure would mean these collisions would occur more often. So,
Yeah,
yeah.
but the downside of having higher pressures, too high pressures, is that we're going to form unwanted species. So in order to excite krypton, which is, I think, I can't remember, it's like almost 10 EV, we're exciting all these other species. And krypton fluorine, we actually have argon in there as well, or neon, depending on your system. And so you start exciting your argon, your neon, and you're going to form all these other molecules as well. So higher pressures was going to form other molecules too. So there's a balance between all of it. Okay, great. So let's talk a little bit more about KRF and ARF. So I'm going to refer us to the Naval Researchers Lab, NRL's Electra system. And this is an incredible system that they have. They have both Electra and Nike. So Nike is their target test bed. And the expert to talk to on this is going to be Matt Wolford. And I do reference a few of his papers, but this is their chamber right now. And these are the numbers I'm going to refer to. So I got a lot of these from their most recent paper, conference paper that was published this year, but don't quote me on everything. There's probably updates that I'm not aware of. So krypton fluoride operates at 248 nanometers. I know I've already shared that, and argon fluoride's at 193 nanometers. Now, the reason KRF and argon fluoride are also just really helpful for fusion is because they have a lot of other benefits. For example, their bandwidth is fairly broad. So krypton fluoride is about 2 to 3 terahertz, and then argon fluoride is actually amazing. It's at 10 terahertz. Um, Pulse repetition frequencies for both these systems, we're looking at hertz. They have gone up to 10 hertz. They just don't get as many shots when they go up to 10 hertz, but we're right in that range. The wall plug efficiency for krypton fluoride's a little bit lower. It's 6 to 7%, so it's still not ideal for fusion, but argon fluoride's at 10% right now, and we're still working on ways to improve both of them. Krypton fluoride in Electra, they were getting 700 joules with these parameters, and argon fluoride was 200 joules. And I know the pulse width for KRF's like 100 nanoseconds. So this is a little bit broad, but they project that the total energy they can get is like it's on the order of megajoules, which is really, really helpful. So there's a lot of benefits. So what should we use? Krypton fluoride or argon fluoride? I mean, right now we don't have as high of energy, but you're going to get better coupling efficiency. It depends. There's more to consider than just these parameters. So argon fluoride, 193 nanometers corresponds to 6.4 EV, and 248 nanometers, 5 EV. So what happens when we get into the UV? It honestly destroys everything. Carmen Manoni out at CSU, she is currently working on optical coatings for these systems because these UV wavelengths, these high energy photons just eat away everything. But specifically with argon fluoride, it actually starts breaking down oxygen bonds in the air. So we have to run everything in a vacuum system, which we're probably going to do anyways, but it takes away the opportunity to run this system in air. And that's going to hurt our wall plug efficiency. So oxygen bonds in the air are around 5.4 EV, nitrogen's almost 10 EV, but at 6.4 EV, you've broken all your oxygen bonds and you formed ozone. So that is one downside on top of there aren't too many good optical coatings that can withstand these energies right now, but it does not mean we can't use the system. It's just an engineering problem that we need to solve. And we have better solutions at 248 nanometers right now. So let's talk about this actual part of the work, which is amplifying these systems. They're great systems. And at some point, I'll try to get Matt Wolford out to give us a presentation and talk about some of the advancements in these systems and the physics. But right now, let's talk about stimulated Brillouin scattering. The reason we're trying to use this as an amplifier for these systems is because it increases the intensities in two ways. The first is that it actually temporally compresses these systems. So we can get them down from like 100 nanoseconds to tens of picoseconds. And I'm not going to go into detail on this. Jihoon gave a talk, I think, in March on this. But if you do have questions today, I saw Jihoon was on, and so feel free to ask and can direct them to him. But the thing that I'm going to focus more on today is that we can scale these systems from kilojoules up to megajoules. So the question is, How do we actually do that? So what is stimulated Brillouin scattering? How does this act? Like, what is this whole process? This is a nonlinear optical process. And so what happens is, I'm going to refer us to this diagram down here. We have a counterpropagating pump and probe. So we have a probe entering this gas cell. And what's going to happen is it's going to form an acoustic wave. And then we'll have a seed laser coming in the other direction. And this acoustic wave acts like a Bragg grating. And what's going to happen is this seed beam is going to be amplified by this acoustic wave. Um, and this process is known as electrostriction, the interaction between an acoustic wave and an optical field. Now you can see right here, there is some frequency dependence on here. So the like the seed beam is going to be slightly different compared to your pump wavelength, and that's going to be determined by your acoustic wave. So optical waves, those are on the order of terahertz. Your acoustic wave, that's on the order of gigahertz. So it's a very, very small shift, but it is something that we see. And this is just another way to look at stimulated Brillouin scattering. I actually found this slide from Creel. So this on this top row, we're seeing this is the input, the pump wavelength, and then counterpropagating, we have the seed wavelength. And as they interact with this acoustic wave, this is kind of what we're seeing. We're going to start seeing this compression. So what are we exactly trying to do? We're trying to determine the gain from this process at low pressures in the UV. And we're going to use these numbers to design amplifiers for krypton fluoride. Now, why low pressures? I mean, UV is pretty straightforward. That's just what the lasers are. Well, there's a few reasons why. Low pressures have a few benefits. One of the biggest ones is it has a higher breakdown threshold. At higher pressures, this number is lower. So we expect to get more gain at higher pressures, but we're going to start to form a plasma in the gas, which is not what we want. So there is this trade-off right here. But another big consideration is the cost. These lower pressures, so less than 10 atmospheres, they're going to be a lot cheaper. Gases are not cheap. So there's a few trade-offs right here. But also, no one's really looked at low pressures either. So how can we make this claim without actually seeing what the gain values are? So what has actually been done? There have been some low pressure experiments done. So this is with argon. The common name you'll see with these experiments is Shea. And we kind of get these profiles going on. So this is the frequency shift between that pump and seed wavelength. And we can see that, oh, there is some gain, but they never actually gave us this value. They left everything in arbitrary units. So we don't know how much gain we can get. And that's kind of the challenge that we're trying to solve right now. Now, the value we're trying to determine, gain, I keep saying gain. It's this coefficient known as the gain coupling coefficient. And it's written right here. It's the inverse of the pump intensity times the effective interaction length between that pump and seed wavelength. And then it's the ratio, the natural log ratio of the energies. So this table right here, this is pretty much the only experiments we've really seen done. And this is at high pressures, looking at 10, almost 40 atmospheres. And some of these are just extrapolated values. So we kind of have at least an upper limit of what we expect the gain to be. But there's no krypton in there. And they use some molecular gases. So there's a lot of data missing. So how are we doing this? This experimental setup was worked on by Stephen, Thomas, and Andre. They've done an incredible job on it. So we have two lasers. We have a pump laser and a seed laser. And these are both neodymium YAG systems. And we are frequency quadrupling them into the UV, so 266 nanometers, which is pretty close to 248 nanometers. So it should give us a pretty good idea of the gain that we can expect in that region. And so we have a counterpropagating pump probe system, and we're measuring the input and output energies with energy detectors. Now, the biggest thing that we need to do is we need to shift that pump and seed wavelength. And this is where this experiment gets really interesting. So the way we're doing that is actually with the cedar. So both are YAGs, and a lot of just solid state systems, crystalline systems, have cedar inside of them. And so this is a very narrow band semiconductor laser. And what happens is this system is the semiconductor laser is heated. It's on a breadboard. And as you heat a semiconductor laser, what happens is the gain medium and the separation between the cavity windows, they're both going to like increase, but they increase at different rates because they're different materials. And so you can slightly shift the wavelength. And so that's how we're observing this gigahertz shifting that we expect to see, is that we start slowly shifting the seed of one of the two lasers with heat. And I don't think many people have thought about doing that before. So, what kind of data do we get? So, this is a plot that a game profile plot that we get, or we've been taking a lot of. So, on the x-axis, we have the frequency detuning. So, again, the separation between that pump and seed wavelength. And on the y-axis, we have the coupling coefficient. And so here, what happens is we get a lot of data points, more than here, but our resolution is around 50 megahertz. So we binned all of our data, and each of these bins, so each of these data points has at least 57 points. Most of them have a lot more than that. So this is for each of these points, you can see the number of data points we've actually collected. And the max for Krypton at 6 ATM, we are seeing around 1.7, we're seeing a gain around 0.22 around a detuning frequency of around 1.7 gigahertz. Another interesting thing is we're starting to see this little bump around 500 megahertz. To the best of our knowledge, at this point, it has no physical meaning. We've looked into several different theories, and it's not what we thought it was. Now, another way to think about this, I mean, centimeters per gigawatts doesn't always mean something to everyone. We can look at this as a percentage. We're getting about 60% amplification at the maximum for these systems. So how does this, change with pressure? So this is now a log scale, so it's not as clear as maybe the other plot, but we can see that as our pressure increases, or in this case, we decreased it, but increasing pressure has increasing gain, and this is what we would expect. Now that peak value, it's pretty insensitive, but it does shift slightly. The shifts become less and less prominent at higher pressures. But this is something really important for us to know because depending on the pressure that we choose, if we want to optimize the gain, we do need to know where is this value. We also start seeing this broadening effect at higher pressures, and we'll start seeing this bump appear more at some of these higher pressures. So this is a very great plot that we're happy that we were able to collect. The lower pressure data, especially 1 and 2 atmospheres, it is a little noisier. SNR is not as great, but it's still very helpful for us. Now, having this experimental data is great, but the downside for it is we need to be able to model it. And so there are 2 theoretical models out there that we investigated to see how does this actually work for these pressures that we're at. The common one that we saw a lot, especially with the higher pressure data, was this theory known as hydrodynamic theory. And this solves the linear Navier-Stokes equation. And what they're modeling is they're modeling like an acoustic wave, and they're saying that we have like a deformation occurring in a fluid. The pressures are so high that you can almost treat it like a fluid. And the profiles we see with the gain are typically Lorentzian. Now, kinetic theory, this is a little bit more complex. We don't see this used as often, but it's the Boltzmann equation, and they have a simple binary collision operator. This theory works great with monatomic gases, and they do have some corrections for the diatomics as well. And with kinetic theory, we're going to get more of a Maxwellian profile. So how do we know which theory might actually work? We can look at the ratio between the acoustic wavelength and the mean free path. And so what happens, higher pressures, the mean free path is going to go down. So hydrodynamic region, that's, I mentioned earlier, we saw that a lot used with high pressures, and that is a theory to use with higher pressures. And at lower gas pressures, it's somewhere like the kinetic regime or the transition regime. But for us right now, we have to see which regime are we in, say at 6 atmospheres. So let's compare the two models with some of our experimental data. So this column right here is at 6 atmospheres for krypton, and this one right here is for 2 atmospheres of krypton. The top row is for the hydrodynamic theory, and the bottom row is for kinetic theory. So, we can see hydrodynamic theory is decent at 6 atmospheres. I mean, it kind of has the peak location, right? But it doesn't have the gain that we're actually observing. It's actually higher than what this theory predicts. And it really starts failing actually at lower pressures. Yeah, it does not match at all. Kinetic theory does a lot better of a job. I mean, it's still not perfect, but it is matching the shape a lot more. Um, we are seeing discrepancies both at the small detuning values, and we'll see some later at the higher detuning values. And it's more prevalent, say, at 2 atmospheres, but our data is also a little noisy. So for us right now, the way to go is kinetic theory, though I will allude to Mazamol's talk later this year. He is working very hard on kinetic theory and is working on corrections to this theory and working on matching it to some of this data. So if you do have questions on it, he's also online today, and I'm sure he'd be happy to answer some questions. So let's look at how our rare gas data is matching with the kinetic theory. So we have krypton here, and I showed the data for this here earlier, but I've not shown argon yet. So these are both log plots. Argon does have lower gain. We can see the kinetic theory fits pretty well. Now, again, this is a log scale. So we can see some discrepancies. Here we have some on the higher frequency side, not really matching the peak. Argon, not as great. Our data is a little bit noisier in argon, but still, it's something for us to work with right now. So this is just another way of looking at the data. This is 6 atmospheres down to a single atmosphere for both these plots, and we have krypton and argon. The red is kinetic theory, and the blue is hydrodynamic theory. So we can see hydrodynamic theory, like we said earlier, just rule it out. And here, this is a better way of seeing kinetic theory is not bad, but like right here, argon, this is a pretty big deviation right here. And it's kind of failing to predict the peaks at for some of these pressures. Now, I mentioned kinetic theory is ideal for monatomic systems, but it does still do a decent job at the diatomic. So we did also look at nitrogen. Nitrogen has a similar gain to argon. And so we can see, there is some discrepancy. Some of it's also just experimental noise. I mean, this broadening that we see, for example, this will be at 4 atmospheres. There's some deviations, but it's doing an all right job. Really, with nitrogen, the hardest part doesn't really predict the peak location as well. So the question kind of becomes, so what gas should be used for these, amplifier systems? And I thought I would make a plot right here and just compare the 3 different gases. So we have krypton, argon, and nitrogen at 6 atmospheres. Sorry, I don't know why these slides keep advancing without me touching anything. So these black curves are the theory, and then the dots are for each of the experimental results. So krypton, as we've seen earlier, it has the highest gain, and it occurs at smaller detuning frequencies. Argon and nitrogen, the gains are honestly about the same, though the frequency separations are different. For each of these gases, the kinetic theory does do a decent job of matching for all of them. We've kind of emphasized that. But we also did these experiments with different testing parameters. We did it with both focused and collimated beam geometries. Focused beams give us higher intensities and higher energies. So we actually get a little bit of cleaner data, but we can see it matches up fairly well. So which gas? It might make sense. Oh, krypton has the highest gain. You guys should just use krypton, right? Well, there's actually a trade-off between the gain and laser breakdown. There's a trade-off for everything when it comes to these laser systems. And so what happens is the laser breakdown value, it increases with the smaller gases. So while we can get higher gain at krypton, The challenge is this, we could start getting to this value, and that would be a problem for us. So does it make sense to use a system with slightly less gain, for example? Um, Neon has this incredible high laser breakdown threshold at 2 terawatts per centimeter squared. Could this be helpful? Now, the gain's going to be a lot less than argon based off of our calculations. Now, we've not done experimental results on this, so this value could be higher, but we actually don't know. So maybe we do something where like we have a two-stage amplifier. We first have krypton get a little bit higher, and then we amplify it a little bit more with a gas that has less. Um, Now, like I said, neon does have a lower uh, gain coupling coefficient. And another issue is neon right now is currently very expensive. The cheapest gases for us to order are always helium and argon. And xenon's just always been expensive. But lately, neon's becoming more expensive than krypton, which is very interesting. Usually it's been the other way around. So that's something for, to look at too, is the trade-off of, does it make sense to go to neon or should we go to argon? Helium just, it does not make sense. You're not gonna, the gain's so much lower and it's not that much more at this point. So we don't know yet what we'll end up using, but we do want to be able to actually study these gases as best as we can. So, what are we trying to do now? We have switched, actually, Stephen has switched specifically these systems to 532 nanometers. So, instead of frequency quadrupling them, he is switching them to frequency doubling. And there's several reasons why. These are some calculations he conducted. We do have less gain in the green, um, but there's a lot of advantages for us just doing these experiments in the green. The biggest issue is we damaged everything in the UV. We damaged all of our optics, the windows of the cell. We damaged our frequency doubling crystals. And this is a pinhole that Stephen was using to filter out the beam. I mean, it's eating away the pinholes. It's truly becoming a challenge for us to do these experiments in the UV. So by switching to 532 nanometers, we're hoping that, now that we've done some experiments in the UV, we can kind of compare and extract them. And we have higher energies at 532 nanometers. And so we should be able to get stronger SNR. We can improve our beam profiles. And we can also conduct saturation experiments. So we can fix, say, the pump energy and see what would happen as we increase the seed energy. And we can do this for several different pump energies, and that will help us with the design. So while working the UV is what we need to do for fusion, we're trying to see if we can switch right here. So we have not conducted any experiments in xenon or neon right now, but we'll see if the system works as great as we hope. Maybe we'll try to do them. We do have some reserve xenon on hand, so maybe we'll see what we can get. So with that, I wanted to make sure I saved lots of time for questions, but I wanted to thank everyone that worked on this project. Like I said, Stephen is really the main workforce on this project. And with that, I will take any questions.
Yeah, I just had a quick question. Can you just
Mhm.
quickly define what bandwidth is and
Yeah,
why that's important?
yeah, that's a great question. So bandwidth is how broad your lasing transition is. So atomic lasers, you're going to see bandwidths on the order of megahertz or gigahertz. Um, I don't really know what they are for some or semiconductor lasers. I primarily work with the gases. So terahertz is obviously an order of magnitude greater than that. But the reason it's so important is the broader bandwidths, it's going to prevent less plasma instability. So when it's really narrow, you're going to be exciting the same transition. And so you're going to create more plasma instabilities. The broader that they are, it's going to help reduce some of those. Does that kind of help?
Yeah, that makes sense. Thank you.
Yeah. And another word you'll see for bandwidth will be full width at half maximum. That's the same thing.
Hi, Kavita. Thank you for nice talk. I
Mhm.
have a question that are you guys interested to work on the binary mixture of the gases in future?
Pardon? The mixing the gases, is that what you said?
Yeah.
Right now we're not looking at that too much. So we have read into some theory on what is expected when we mix gases, and they expect it to just be a linear superposition right now of the gain. And so for that
Uh,
value, it
mm,
doesn't really make sense. But in
no.
terms of the physics, that could be really interesting of how do these, I guess I should say at first order, they expect it to just be a linear combination. But
Yeah, but
there's probably
linear.
going to be some interesting interactions, especially as you get to higher pressures. But 6 atmospheres, I don't think you're going to see that. Maybe like at 10, 20 atmospheres.
Yeah, but linear superposition that comes a linear combination of these two when the masses are equal. But if you have some different masses, then that comes with a different maybe due to that.
There could be a little bit of something, but to our understanding, at least the gain is going to be a linear superposition, based off of calculations Stephen's done. So we'll see. We'll see how much gas we have left at the end of the experiments if we want to try mixing them. But at this time, we're not. It's also challenging to mix two gases in a cylinder and know exactly what their partial pressures are. So we'd have to buy a specific gas mixture with that, which could take some time, especially with krypton. Krypton leads can be as long as months. So
Okay.
mhm. That's a great question, though. Any other questions from anyone? It can be it can be very general, it could be very specific.
I have a quick question.
Yeah.
When does like the hydrodynamics theory just doesn't seem to work very well? Does it ever like agree with the kinetic theory result at some point, or do you know why they don't agree?
That is a great question. So it's two different theories, two different ways to model the system. I believe hydrodynamic theory really does work well at 10 atmospheres, which is what they used um, in these experiments. They used the hydrodynamic theory right here. Now, do they converge? I have not studied kinetic theory too much. Maybe Muzzlemal knows more about this. He studied this a little bit more than I have. Based off of these plots right here that I'm seeing, it does look like the theories do start to converge a little bit. Um, but like I said, I'm not the expert on that. Muzzlemal, I don't know if you have anything you want to add.
Yeah, I just want to say that this is theoretically, if you will work on the linear Navier-Stokes equation, that is not too much different from the Boltzmann equation. In the Boltzmann equation, with the where you have the kinetic theory, the coupling coefficient is very important to understand that. And in that coupling coefficient, we have to introduce some perturbations, due to which we are getting the more gain and more accurate results with respect to that instead of the hydrodynamic theory.
Thank you. And for anyone else that's on here, Muzzleman, like I said, is working on that theory. And then Jihoon's working on the temporal side of this theory. So it's been a fun collaboration with all three of us. Not me, really, Stephen in there.
Kavita, great talk. Thank you. I had a question.
Mhm.
Who else has high power krypton lasers? Naval Research Lab, Exemer is building one. Who else in the world has really high power Exemer lasers?
I don't know about the world, but in the US, it's just those two that I know of. Yeah.
Okay.
There's only one manufacturer, krypton fluoride lasers. They use them a lot, lower power systems for a lot of surgeries. And the only manufacturer in the US of a discharge pump system is Coherent Energy, and they'll make custom systems for that. But that's the US. Um, there's probably one or two on the other side of the world, but they're not easy systems to work with. I will say that fluorine is not a gas I recommend working with unless you have to.
Great. Thank you.
Yeah. Oh, I should say, Los Alamos, I think at one point did have a KRF, but they got rid of it in the 90s. Um, so I think they had one though. Any other questions from anyone? Well, I will stop recording.